Okay, so in previous chapter was about cyclic groups. Now we will talk about the permutation groups, and this one is more interesting, and it's all the talk about the symmetries and that kind of stuff. So, quote, symmetry has been the scientist's pillar of fire, leading towards relativity and the standard model, said by Mary Olivio in the book The Equation That Could Not Be Solved. Okay, so we start with the definition and notation. So in this chapter, we will we study certain groups of functions called permutation groups from a set A to itself. And mid in early and mid 19th century, groups of permutations were the only groups investigated by mathematicians. It was not until around 1850 that the notion of an abstract group was introduced by Cayley, and in and it took another quarter century before the idea firmly took hold. So the we present the definition of a permutation groups. So definitions. What we call by a permutation of a group or a set first for permutation of A and then permutation group of A. Okay, so a permutation of a set A is a function from set A to A that is both 1, 1 and onto. So a permutation of a set A is a function from A to itself, or A. I can write bijective, but that is both 1 to 1, 1 to 1, and onto. So then a permutation permutation group of a set A is a set of permutations of A that form a group under function composition. Under function compositions. Perfect. We know what is a permutation, and then we can construct by combining all those permutations of a set and use the operation composition to create a group. Okay. Now, although groups of permutations of any non-empty set A of objects exist, we will focus on the case where A is finite. Okay. Furthermore, it is customary as well as convenient to take A to be a set of the form that of the form. So we take A to be a set of the form 1, 2, 3 up to n for some positive integers n, for some positive integer n. Okay. Now, unlike in calculus, where most functions are defined on infinite sets and are given by formulas in algebra, permutations of a finite set are usually given by an explicit listing of each element of the domain and its corresponding functional value. For example, we define a permutation alpha define a permutation alpha of the set 1, 2, 3, 4 by specifying that alpha of 1 goes to 2, alpha of 2 goes to 3, alpha of 3 goes to 1, and alpha of 4 goes to 4. Perfect. Now, more convenient way to express this correspondence is to write alpha in array form. So you can use the capital brackets or braces only to denote it. So let's say alpha can be written as, we have domain here 1, 2, 3, 4. We write the images in the second row, which is 2, 3, 1, 4, like this. Now here, alpha of j is placed directly below j for each j. Okay, so that is the trick. Similarly, the permutation beta of the set similarly we write permutation beta permutation beta of the set which has 6 elements inside it, right, given by, if I just use the the array notation, I should say here array notation. If I just give the beta in the array notation, that is going to be that I have 1, 2, 3, 4, 5, 6, and then low we have 5, 3, 1, 6, 2, 4. This means 1 goes to 5, 2 goes to 3, 3 goes to 1, 4 goes to 6, 5 goes to 2, and 6 goes to 4. That is the permutation beta. Now composition of permutations expressed in array notation is carried out from the right to the left by going from top to bottom and again from top to bottom. So let's say we have sigma. Let's write composition, or like let's first assume let sigma and gamma are permutations of the set 1, 2, 3, 4, 5, and we denote them as sigma can be written as that 1 goes to 5, sorry, 2, 2 goes to 4, 3 fixed, 4 goes to 5, and 5 goes to 1. Okay, and then comma is written as 1, 2, 3, 4, and 5, 4 and 5, and we can send 1 to 5, 2 to 4, 3 to 1, 4 to 2, and 5 to 3. Okay, then when I want to compose gamma and sigma, okay, what I would do, then composition is given by gamma compose sigma is given by, we have 1, 2, 3, 4, 5, and then have 1, 2, 3, 4, 5, right? Here we will write the answers. So we write the domain first, 3, 4, 5. Now, the gamma, let's first write the gamma. The images are 5, 4, 1, 2, 3. And then sigma has 2, 4, 3, 5, and 1. Then we would pick one from here. So we would pick, let's say, one from here. So this goes here. We pick one from here, and then this goes. So we would say 1 goes to 2. Now we would check 2 in this permutation over here. We trace it here, and then we say 2 goes to 4. That means 1 goes to 4 here. Perfect. Now we have reached 4. Now we would check 4 goes to 5 in this permutation, and now we would check 5 goes to 3. So that means 4 goes to 3. Okay, then we reached 3. Now we would check 3 is fixed here. Okay, then we would check 3 here, which goes to 1. That means 3 goes to 1 in this one. Now we have reached 1 again. Okay. And we know 1 goes to 4. Now we will check for 2, let's say. So we'd see 2 goes to 4 here, and then 4 goes to 2 here. So that means 2 goes to 2 here. Perfect. Similarly, we are remaining with 5. Now 5 goes to 1 here, and then 1 goes to 5 here. So that means 5 goes to 5 here. This is the way of composing the permutations using the cycle notation. Now, we can do similarly by using the function notation and check that y compose sigma, what will be the image of 1. So we check first what is the sigma of 1. So sigma of 1 is what? 2. And then what is the gamma of 2? Gamma of 2 is what? 4. So that's why 1 goes to 4 here. That is the way of composing two permutations. Right? Perfect. Now we are now ready to give some examples of permutation groups. So let's give an example because we know how to compose things, right? So example 1, we call this example symmetric group, and we denote it with S3. Okay. Now we say let S3 denote the set of all one-to-one set of all one-to-one functions from set 1 to 3 to itself, right? Then S3 and the function composition is a group with 6 elements. 6 elements. The 6 elements are of, now we know two notations, either function notation, second array notation. At this time, we would use array notation. Let's call the first composition epsilon, which would do what? Which would fix everything. Okay, we call it identity. Then we write alpha, which would send 1 to 2, 2 to 3, and 3 to 1. Then we would do alpha square, which would do send 1 to 3, 2 to 1, and 3 to 2, right? And then we would do beta, let's call this beta, which is 1, 2, 3, which would fix 1, send 2 to 3, and 3 to 2. And now let's do alpha beta. This is a composition. Okay, this is a composition. You get this thing with composition. Alpha sends 1 to 2, 2 to 1, and it fixes alpha beta. Okay, then we would do alpha square, beta square, sorry, beta only. Then it is one, it sends 1 to 3, fix 2, and 3 to 1. Perfect. Now note that S3 is not abelian, which is what? Which means what? Means that when you compose, when you do beta alpha, when you do beta alpha, that is a permutation which is 1, 3, 2, 2, 3, 1, and it is not, it is equal to alpha square beta, but not equal to alpha beta. Okay, so that S3 is not abelian, not abelian. Okay, perfect. Now the relations, okay, this is the example S3. You can find the inverses. So alpha is inverse of alpha square, and they both are inverse to each other. Beta is inverse to each other. Okay, and alpha beta are inverses to each other. Alpha square beta are is inverse to each other. So they are like this. Okay. Now the relations, we can use these relations like this kind of relation. The relation that beta alpha is equal to alpha square beta can be used to compute other elements, other compute other products in S3 without restoring to the arrays. Like we can say that beta alpha square is going to be beta alpha into alpha, right? And this is going to be beta alpha is nothing but alpha square beta, and we have alpha here, and this can be written as let me, this can be written as, so let me, I need this bit, so I want to write this thing on a new line, and then we can write that this is alpha square beta alpha, right? And we can again write alpha square is out, alpha square beta alpha, right? And then I can say this is alpha power 4 beta, but alpha power 4 is nothing but alpha, which is alpha beta. So beta alpha square is equal to alpha beta. An example, and this SEM S3 can be generalized as follows. So we say that now we'll generalize this example. In example 2, which is symmetric group Sn. Now, this is that let A be the set 1, 2, 3 to n of n objects, the set of all permutations of A is called the symmetric group of degree n and is denoted by Sn. Now, do you realize why we call it symmetric group? Because when you look at these symmetries, these epsilon, alpha, alpha square, beta, alpha beta, and alpha square beta, for a simple example, for a very small example on 3 elements, you can spot the symmetries in these permutations, right? So they are nothing but symmetric things. Symmetric permutations are like they give you the symmetry when you send 1 to 2 and 2 to 1 in alpha beta, or when you send 2 to 3 and 3 to 2 in beta. Okay, they give you the symmetry, and each of these permutations is nothing but a symmetry. It's kind of a symmetry of these numbers. Okay, you can do something to them and can get back to the original position. That's why when we collect all these things, all these kind of permutations, and that's why we give the name to the group symmetric group. Okay, perfect. Now elements of Sn of Sn have the form that it is a permutation alpha in the array notation, which is 1, alpha of 1, 2, alpha of 2, so on, and alpha of n, right? Now it is easy to compute the order of Sn. There are n choices of alpha of 1. Once alpha of 1 has been determined, there are n minus 1 possibilities of alpha of 2. Since alpha is a 1-to-1 function, we must have alpha of 1 is not equal to alpha of 2, right? And after choosing alpha of 2, there are exactly n minus 2 possibilities for alpha of 3. In computing along this fashion, we see that the order of Sn has n into n minus 1 up to 3 to 1, which is equals to n factorial elements. And Sn is in general is not an abelian group. And these symmetric groups are very rich in subgroups. Like if you take a symmetric group on 4 elements, as we will call it S4, it has 30 subgroups, and S5 has well over 100 subgroups. So they are very well rich in subgroups. So I should write, if that works, the group S4 has 30 subgroups. S5 has over 100 subgroups. Interesting. Now let's present in another example for a particular way, and we we have done this before, but we would do in a different way now. Remember, we did symmetries of a square in chapter 2 or 1. So now we had eight elements in the symmetries of we had eight symmetries in the symmetries of for the square, and we can associate a motion in D4 with the permutation of the locations of each of the four corners of a square. And for example, if we if we have if we have a square, should be square. Why it is rhombus? Okay, I guess my iPad and me are very bad in the writing and drawing. Okay, so let's say 1, 2, 3, 4, and we call it epsilon identity. And let's say we want to write a permutation, other permutation, that is 3, 2, 4, 1. How do you associate this one? And let's write this row in array form. 1, 2, 3, 4. Now you can see at the position of 1, at the position of uh, so we have 1 here and 2 here and 3 here and 4 here, an actual one in the identity one. Okay, and now we have shuffled the row, and now row says you have at the position of 1 you have 2, at the position of 2 you have 3, at the position of 3 you have 4, and the position of 4 you have 1. So this is the permutation row in the array notation. And let's say where is the reflection across the horizontal axis. So this is a permutation we call row is a 90-degree counterclockwise rotation. Okay, now a reflection across a horizontal axis yields this identity square to a square, let's call it phi. Okay, let's first write phi in the array notation, or like, okay, so this says 1 we have 2, at 2 we have 1, at 3 we have 4, and at 4 we have 3. And that is 1, 2, 3, 4. 1 goes to 2, 2 goes to 1, 3 goes to 4, 4 goes to 3. Right? Now these two elements generate this entire group. You can write these two elements generate the entire group. So that means every element is a combination of alpha and phi. Okay. And you can say D4 would have elements by this is E, rho, rho square, rho cube, and then phi, rho phi, rho square phi, rho cube phi. Okay, perfect. And then you can write these. Rho square is the rho composed rho, rho cube is a rho square composed rho, something like that. Okay, perfect. Then you can say D4 is a subgroup of S4 when written in this form. Okay, perfect. We would end this lecture. Yeah, thank you so much.